Hi, my name is Urs Holzle, and I'm going to talk about a third-generation self-implementation, and especially how we combined responsiveness with efficiency in that implementation. This work was done together with David Unger at Sun Microsystems Laboratories. Today, programming environments should have at least two attributes. First, they should be responsive. That is, they should react immediately to your commands. So if you change something, you don't want to wait for a compiler or linker to catch up with you until you can try out the effects of the change. And that is important because you want to concentrate on your task, on developing your application, and you don't want to be distracted by the environment or by pauses created by the environment. The second attribute that we want is efficiency. And in this programming environment should run your programs as quickly as possible. And together, these two attributes try to maximize your productivity, because a programmer's productivity is what counts in a programming environment. Now, there's many other aspects of programming environments that I'm going to ignore in this talk, like user interface issues and so on. So today, I'm just going to be talking about responsiveness and efficiency. Now, unfortunately, responsiveness and efficiency are conflicting goals, because in order to be efficient, we need something like an optimizing compiler. And that's especially true for a pure object-oriented language like Self or Smalltalk. Now, on the other hand, in order for a system to be responsive, we don't want an optimizing compiler. We want an interpreter, because an interpreter doesn't give us any pauses. And so it seems, if we look at this graphically, that efficiency and responsiveness are two orthogonal axes, and we can be either up near the y-axis with a batch environment where we have good efficiency but not so good responsiveness, or we can be near the x-axis where we have an interactive exploratory programming system but we don't have good performance. And of course, where we want to be is up in the right-hand corner where we can have both. Now, in this talk, I'm going to tell you how we tried to go to the upper right corner in the Self 93 implementation, and how to have both performance and responsiveness in the same system. So what I'm going to do in this talk is I'll give you an overview of the Self implementation, and I'll tell you how we tried to achieve both responsiveness and performance and combine them in the same system. And mostly, I'll be talking about the responsiveness issue. The performance we discussed in another paper at PLDI 94. So if you're interested in the particular compiler optimizations, then please go and read that paper. And in this talk, I'm mostly going to focus on the interactive aspect on responsiveness. And a second part of the talk will be pause clustering. That is, how do you evaluate a system that creates pauses, and how do you measure these pauses in the interactive system? But first, let's go back to the implementation. Of course, people have long tried to be in that upper right-hand corner of this graph, and have tried to have a responsive and efficient system. And in fact, 10 years ago, Peter Deutsch and Alan Schiffman presented a Smalltalk system that improved on the previous interpreters that were too slow in the efficiency domain by introducing dynamic compilation. The idea here is to compile a source method into machine code the first time it is called. And so the first time it's called, it's being translated into machine code, then that code is being cached, and so the next time you call it, you directly execute the machine code. The advantage of that scheme is that it eliminates the interpreter overhead, and therefore your programs are going to run faster. And in the system that Peter Deutsch and Alan Schiffman presented, the compiler was very fast, and so the system still stayed responsive. Now, unfortunately, the fast compiler didn't do much optimization, and therefore the resulting programs, while they were faster than an interpreter, were still not very efficient. So the next step, obviously, is to try and use an optimizing compiler with dynamic compilation, and to use dynamic optimizing compilation. That was first introduced in the first two Self implementations in 89 and 91, presented by Chambers and Unger. The idea is exactly the same. So the first time you call a particular method, it's being translated into machine code. But this time, we use an optimizing compiler to generate the code. And therefore, after that, we can run optimizing code. Programs will run faster. Now, unfortunately, using an optimizing compiler in an interactive programming environment is not an easy task because of the pauses that are being introduced by the compiler. To show you what happens when you use an optimizing compiler in an interactive programming environment, I'm going to show you an example from Self, namely the Self programming environment that consists of about 15,000 lines of Self code. And I'm going to show it running under the Self 91 system that always optimizes all code. Now, just before we start this example, I manually removed all compiled code from the system. So now the first time we do anything, the compiler first has to generate the code that executes the action we're actually interested in. The first thing I'm going to do is dismiss this editor object here by pushing the dismiss button. And now the editor window should disappear, but as you can see, nothing happens. And that's because right now the compiler is compiling all the code that is needed in order to make the object disappear. But finally, the button goes down, and the editor will disappear. Now I'm going to pop up a menu here. And again, there's a significant distracting pause because the compiler has to generate new code. Of course, the second time you do something, the compiled code is there, and here the menu pops up immediately. Finally, I'm going to display the contents of this object slot here. And again, there's a significant distracting pause. Now, the problem here is not that we're running on a slow machine. This is the SPARCstation 10. And it's also not that we're having a slow compiler. The compiler is as fast as an optimizing C compiler. The problem is that in an interactive environment, a pause of 10 seconds is very long, whereas in a batch environment, you're very happy with a pause of 10 seconds. So in an interactive environment, the demands of the user are much more stringent. And therefore, normal compilation speed is not good enough. Now, what can we do about this? What we did in Self 93 was to introduce adaptive recompilation. And the main idea here is to not always optimize everything, but only optimize the hotspots of the program. So only optimize when necessary. The first stage is exactly the same as in standard dynamic compilation. The first time a method is invoked, it is being compiled into unoptimized machine code. And then only if it is executed often is it optimized by a second optimizing compiler and transformed into optimized machine code. So this system uses two compilers, a fast non-optimizing compiler and a slower optimizing compiler. Now, why is this good? Why does this reduce compile pauses? There are several reasons why adaptive compilation reduces compile pauses. The first one is that the pauses introduced by the optimizing compiler are more spread out over time. They don't all happen in the beginning when you start some new code. Second reason is that the non-optimizing compiler can be much simpler and therefore much faster than an optimizing compiler. And in fact, it is more than an order of magnitude faster than the optimizing compiler. And therefore, it's able to generate the initial code much more quickly than any optimizing compiler could. And finally, our optimizing compiler can also be faster than the previous compiler because of the compilation techniques it uses, especially because of a technique called type feedback. And that technique I don't have time to go into, but if you are interested, you can go and read my PLDI 94 paper. Now, to go back to our original goal, we wanted to be in that upper right-hand corner of this graph and have both responsiveness and efficiency. The PLDI paper I talked about demonstrates that our efficiency is as good and, in fact, about 50% better than the efficiency of the previous system. And in the next segment, I'm going to show you that our responsiveness is almost as good as that of an interpreter. So first, I'm going to make this editor here disappear by pushing the dismiss button. And as you can see, the pause is much, much shorter than it was before. I'm popping up this menu. It comes up almost immediately. And I'm displaying the slots contents of this object here. And again, the reaction is almost as good as an interpreter. There is a slight pause, a slight hesitancy, but code reacts very quickly to the user's demand. Now, one place where this is important is when changing programs, because a change invalidates existing code, and so the compiler has to recreate compiled code. What we have here is a text editor, and a text editor has a scroll bar on the side, and if you drag the scroll bar, the text scrolls as you would expect. Now, this object up here is implementing scroll bars, or sliders as we call them in Self. What I'm going to do now is I'm going to edit the method that returns the position of the slider. And I'm going to change the return value to essentially invert the sense of the position. So instead of saying top, it's going to say bottom. Instead of saying bottom, it's going to say top. Now before, I still haven't actually accepted that change, so the scroll bar still works the way we expect it. But after I accept the change, the system automatically invalidates all compiled code that is affected by it, and I can go and immediately try out the change. And you can see I didn't have to wait. Now, how does this actually work? How does the system recompile methods as needed? There are two problems that we need to address. The first problem is that the system needs to detect when performance is bad. So we need to detect that something needs to be done. And the second problem is what to do in that situation. So how to best improve performance. First, let's look at when to recompile a method. So how do you detect if we're spending too much time in unoptimized code? What the Self93 system does here is very simple. It measures the invocation frequency of methods, of unoptimized methods, by introducing an invocation counter into each method. So every time a method is called, this counter is incremented, and if it exceeds a certain limit, the recompilation system is being called. Now, a more important problem is, and a more difficult problem is, what to recompile. How can we select a good candidate for recompilation with the intent of removing as much overhead as possible from the unoptimized system? Now, one obvious way of choosing the method to recompile would be to just choose the method that overflowed its counter, because obviously that method was executed very often. However, that is not the right solution, because you could have a method, for example, this method executed often here, that just returns true. And by optimizing this method, you're not going to gain very much, because the unoptimized code for returning true is almost as good as the optimized code. So what you really want to do is have the compiler inline this method into the caller. So let's look at an example. Here's a stack of an executing program. Stack goes downwards, so A calls B calls C. Now let's assume that C just triggered its recompilation counter. So the system looks at the stack and tries to find a good method to recompile. There are several criteria that are used to select methods, and several heuristics that try to find the best method to recompile. These heuristics, in general, look at the size of the methods. So how big is the method? Is it likely that it's going to be inlined into its callers? How many sends does the method perform? And finally, does it contain any loops, or does it create any closures that are used often in its callees? In this example, the compiler would probably skip the C method because it only increments a variable, and so it's very small. It's likely to be better if we inline it into B. And then it might discover that A is really calling B within a loop, so what we should do is recompile A and optimize the entire loop. So let's assume that's what the system does, and it recompiles A, inlining B and C, and therefore what we have in the optimized situation is just one stack activation with A and B and C all inlined into the same method. So what's happening is that step by step, the recompiler will optimize parts of your call chain, and therefore the program will become faster and faster as we go along. Let's go back to the original picture and look at the responsiveness. What we wanted to do is combine responsiveness and efficiency. And so we need to have a way of evaluating the responsiveness of our system and measure the compile pauses that it introduces. Now, how do you measure a compile pause? What we really want to do is capture the user's experience. That is, what kind of pauses does the user see that are caused by the compiler? Now, what I claim here is that the raw pause times, so the pauses that are actual compilations, are almost meaningless for characterizing the interactive performance of a system. Why is this? The problem, or the fact, is that if two pauses occur in very short succession, let's say separated by only 10 milliseconds, the user is not going to be able to tell that there were two individual pauses. What the user is going to see is one longer pauses. And so to evaluate the interactive behavior of a system, we need to cluster our pauses into groups if they occur in short succession. So down here in this example, you see lots of small pauses that occur in very short succession. And instead of these lots of small pauses, what the user is going to see is one longer pause. And then over here, there's another pause, because that compilation is by its own. That we define pause clustering as an attempt to capture that effect, the effect that the user sees pauses cannot distinguish individual pauses if they occur shortly in short succession. In effect, what we're doing is we're trying to group all these pauses into longer pauses as long as they fulfill two rules. The first rule, or the first condition, is that no gap within a cluster should be longer than a certain time interval. The time interval we chose was half a second, so we assume that if two pauses are half a second apart, the user is going to be able to tell that there are two different pauses, and therefore we don't group them into the same cluster. The second rule is that the actual pauses within a certain cluster need to make up at least a certain percentage of the total time. What we've chosen is 50%. So at least 50% of a pause cluster needs to be real pauses. Or another way of looking at it, at least the system needs to slow down by at least a factor of 2 in order for it to count as a pause. Because if we have 50% of the cluster being pauses and 50% being the gaps between pauses, the system is still running at half of its normal speed, and the other half it's spending in compilation. Now, what kind of a difference does that make in a real system? We have measured the self-system and seen the impact of pause clustering. This graph here shows the pause length on a Spark Station 2 on the x-axis and the percentage of all compiles that exceed a given length on the y-axis. Now, if we asked, for example, how many pauses, what percentage of our pauses exceed 0.2 seconds, the answer is going to be either less than 1% if we measured individual pauses, or way more than 20%, 30% in fact. So the difference between the two answers is enormous. And in fact, over the entire range of pause lengths, the two answers are going to differ by at least a factor of 10. So if anyone characterizes an interactive system based on individual pauses, their answers are probably going to be too optimistic by an order of magnitude. And therefore, it's very important to use pause clustering whenever you measure pauses in an interactive system. Now let's look at the self-system and use pause clustering. We've measured the pauses that happen during a 50-minute interaction with the system and drawn this diagram here. Again, on the x-axis, you have the pause length. This time on the y-axis, you have the absolute number of pauses that exceed a certain length. And the y-axis is a logarithmic axis here, so because we have such a big range. What we can see is that the uppermost curve for the Spark Station 2 shows us that, for example, about 20 pauses are exceeding 1 second. So only about 20 pauses during these 50 minutes exceeded a 1 second length. If we go to a faster machine, like a SPARCstation 10 that is 3 times faster than the SPARCstation 2, the pause behavior improves even more, and only about 10 pauses are going to exceed 0.5 seconds. And if we go to an even faster machine, like the ones that are being announced now for 1995, only very few pauses are going to exceed 0.2 seconds. And so on such a machine, the system will behave almost like an interpreter, and the pauses are going to be almost unnoticeable. Now, I say almost because there's still one place where you can notice the effect of compilation, and that is when starting up large applications. If you start up a large application with no precompiled code, the system takes a while until it gets up to speed, until it has recompiled the hotspots of your application, and until you reach normal levels of performance. What we've seen is that typically the startup time is roughly proportional to the size of the program. And on a SPARCstation 2, it takes roughly about 1 minute for a 10,000 line program to get up to speed. So that doesn't mean you have a pause of 1 minute. What it means is that the system will be slower than normal for about 1 minute until it approaches the asymptotic performance. Now, this is normally not a problem, because the only time you really have no code for a large application is when you made a change that invalidated large amounts of compiled code. So for example, if you go and change a very basic method, like integer plus, it's going to invalidate a large portion of your program, and you have to recompile. And that's when you see these pauses. But the good news is that when you deliver an application to your customer, you're not going to be bothered by such pauses, because you can include optimized code with your application. And so the user is never going to start from scratch with no precompiled code. So let me come to the conclusions. What I showed you today was that the Self 93 system can combine very good performance and almost interpreter-like responsiveness by using adaptive recompilation. The system can be so interpreter-like not only because of adaptive recompilation, but also because of advances in hardware. It really needs a roughly 50 spec int processor to keep the pauses under a certain absolute time, which is very important because above about half a second, pauses tend to get very distractive to the user. And so if your system, as long as your system has the necessary speed, your interactiveness will be good. And in fact, in the future, with faster and faster machines, we will be able to get even closer to an interpreter-like system, even though we're using an optimizing compiler. The second point that I made in this talk was that when you want to evaluate the pause behavior of an interactive system, you have to use pause clustering. Because if you're having many very small, short pauses that occur in short successions, just measuring the raw pauses will be a very distorted picture of the interactive behavior. And only if you use clustered pauses will you see the real pauses that the actual user will also see. Now, before I finish, I'd like to thank a lot of people that have contributed to the Self system. In particular, I'd like to thank Lars Bach and Beiwei Chang for helping me to make the videos that you saw today, and all the other members of the Self group for contributing to the Self project. And finally, if you'd like to know more about Self, there are many papers and the actual system available through Mosaic or FTP from the addresses shown here. And so if you'd like to know more, just look into our archive and you'll find a lot of papers and additional documentation. Thank you for your attention.